In this photo, NASA astronauts in pressurized gear aren't floating in space. They are 20 meters below the surface, living in the Aquarius Reef Base. Every year, NASA sends these researchers, dubbed Aquanauts, down into the depths for weeks at a time, as part of Project NEEMO. They use the seabed to simulate the isolation of a long-term mission, practicing with autonomous vehicles and executing complex repairs on the ocean floor. At these depths, the environment is defined by weight. For every 10 meters you descend, the pressure increases by a full atmosphere. When that pressure becomes too great, the results are instantaneous. The Titan submersible imploded in less than a millisecond, long before the human brain could even register a sensation of pain. NASA is studying these extreme environments because they provide a terrestrial laboratory for the physics and logistics required to explore an alien world. The crushing depths of Earth are the proving ground for their ultimate destination. This is Jupiter's moon Europa. While the surface is a desolate shell of solid ice, planetary data suggests a vast liquid environment beneath the crust. On Earth, we know that life doesn't require sunlight to begin. In the Hadal Zone, miles below the reach of the sun, entire ecosystems thrive around hydrothermal vents, feeding off the heat and minerals released by underwater volcanic activity. Europa likely possesses its own version of these vents through a process called tidal flexing. As Europa orbits Jupiter, the gas giant's massive gravity constantly stretches and squeezes the moon's core. This physical distortion creates friction, which generates a massive amount of geothermal heat. That heat radiates upward from the core, melting the underside of the outer ice shell. The result is a global saltwater ocean that contains twice as much liquid water as all of Earth's oceans combined. This environment provides the three components we associate with the development of life. First, liquid water, consistent energy from the core, and a chemical inventory of elements like carbon, oxygen, and sulfur detected on the moon's surface. While Europa is the most promising candidate for alien biology in our solar system, reaching that water requires humanity to overcome four distinct engineering hurdles. The very first hurdle is the distance. This is the Europa Clipper, the spacecraft NASA has built to cross the hundreds of millions of miles between Earth and Jupiter. There is no rocket powerful enough to fly in a straight line to the outer solar system. Instead, the spacecraft has to steal momentum from the planets themselves. The Clipper will spend 7 years performing a gravitational slingshot maneuver. It will loop past Mars and back toward Earth, using their gravity to catapult itself toward Jupiter at incredible speeds. This requires projecting the exact future positions of every planet years in advance. The navigation team must calculate entry angles with extreme precision to ensure the craft survives the journey through the asteroid belt and arrives at the correct window in space. Navigating this celestial pinball game only gets the spacecraft to the edge of the Jovian system, where it faces a second, more violent challenge. The second major hurdle is the arrival. Jupiter's gravity well is so powerful that any craft approaching it will be accelerated to speeds that make entering a stable orbit nearly impossible. To slow down, the Clipper will weave through Jupiter's 4 largest moons. By flying close to these massive bodies, the spacecraft will use their gravity as a brake, scrubbing its velocity until it can safely settle into orbit around Europa. Once the orbit is established in 2031, the probe will begin mapping the surface, measuring gravity values, and analyzing the thin atmosphere to find the best point of entry. Mapping Europa is a massive achievement, but finding proof of life requires physically penetrating the ice. This leads to hurdle 3, the ice barrier. The liquid water we're looking for is trapped beneath a frozen crust that engineers estimate could be up to 20 kilometers thick. To bypass this, future mission designs propose a cryobot. This probe would use a nuclear heat source to melt a path through the ice, slowly sinking through the crust over the course of several years. If the cryobot reaches the bottom, it faces hurdle 4, the pressure of the alien ocean. The weight of the water at this depth would be immense, requiring hardware that has been tested in our own deepest trenches. At this stage, the probe would deploy 48 autonomous microrobots. This swarm would swim through pitch-black water, searching for heat signatures of hydrothermal vents. Melting through miles of ice to deploy an autonomous submarine swarm represents the most ambitious robotic sequence in human history. Our search is currently framed by what we know about Earth. It is possible that alien biology functions without water or DNA, which means we could be searching for the wrong signatures entirely. But the value of the mission remains. The effort to solve these engineering problems drives advancements in robotics, material science, and navigation that benefit our civilization regardless of what we find in the ice. Pursuing a 1% chance of discovering life beyond Earth is a testament to human curiosity. That drive to explore the unknown is what unites us and pushes our technology into the future.